So, as I was saying, we plotted the foci here and here. They gave us one, but they're symmetric. And put the vertex they gave us here, but there's one 4 the other way as well. A is 4 because the vertex is 4 away from the center, and A is the distance to the vertex. C is 3 because the focus is 3 away, and that's what C represents. Now we need to find B using Pythagorean theorem. And once again, you can write it kind of as an addition, where A is the biggest, like that. But frankly, you just want to rearrange it to find B. It would be A squared minus C squared, because A is the biggest, right? A squared is 16, C squared, that's that. Yeah. 16 minus 9 gives you 7, square root of 7. Now on the graph, first of all, you tell me, square root of 7 is how big? 1 point something, 2 point something, 3 point something, what? It's more than square root of 4, but less than square root of 9, so 2 point something. So all I expect you to do is know that and put it somewhere between 2 and 3 on the graph. And down here, do the same thing. And now, draw your ellipse through those points. Be careful. Last period, I went through the foci. It doesn't go through the foci. The foci are never a point on the graph. The vertices are always a point on the graph. Okay, this is not a very good ellipse. Yes, that's what I'm saying. It's symmetric. The center is halfway between the endpoints of the minor axis. Now, there's our graph. We need the equation now. The form, it's always, here, let me write the form up here. It's x minus h squared for one numerator, plus, always a plus sign for an ellipse. For hyperbole, that'd be a minus sign, by the way. So get that right. What goes here always? 1. So remember, that's always a 1 for an ellipse. And then your denominators are a squared and b squared. In our case, it's horizontal, so a squared is this denominator, b squared is that denominator. But I'm saying here, ours is special, though, because the center is the origin. You won't have x minus something squared. It's just x squared for one numerator. And same for the y. It's y minus 0 squared, but that's just y squared. That's always a 1. And then a squared is 16, and it goes under the x because the 4 is horizontal. And b squared is 7, and it goes under the y because b is vertical, and we are done. Except for one more thing. I want to find the eccentricity of all these ellipses as we go through this. So, eccentricity is found by doing C over A. So, 3/4. Which is around 0.75. In here. I'm trying to keep track. By the way, just a note, if you want to type this in the calculator, you can't until you solve for y. And just think, follow along. I'm just going to do the algebra mentally. To get y by itself, first you subtract the x squared over 16 from 1, move it over. That's where this comes from. You get rid of the division by 7 by multiplying by 7. And you don't have to multiply through, just did like they did, multiply by 7 with parentheses. And then that point you have y squared by itself, so you take square root, but remember, you get plus or minus. And if you typed in the positive version, you get the top half of the ellipse. You put in the negative version, you get the bottom half of the ellipse. And so you can get in the calculator without fairly too much trouble. You should be able to do this mentally to get that equation in the calculator if you want to. Check your answers. That would be an Australian football field. All right, this one. Do you have this one? Let's see what we can do without drawing the graph. Okay? First of all, is the major axis horizontal or vertical? And look at it. These 2 points are on what kind of line? A horizontal line or a vertical line? They have the same y value, right? In fact, write this down. The major axis has the equation y equals -2. Because both points have a y value -2. What's a horizontal ellipse? The minor axis, these 2 points are both on that axis. They have an x value 2, so the equation is x equals 2. It's a vertical axis. And it'd be easier to figure this out if you drew it first, but I'm saying I'd like it if you can figure it out just from this. Let's go a step further. So the center is the point that's on both axes. So what point is on this axis and this axis? 2, -2. Every point on this line has an x value 2. Every point on that line has a y value -2. So the center must have those coordinates. Okay? Now, let's go ahead and draw this thing, and then we'll go get the equation. Actually, before we do this, I want to go a step further. By the way, the major axis, we normally talk about its length, and it's 2a in length. How far apart are these endpoints of the major axis? From -1 to 5 is 6 away, yes? So a is 3. How long is the minor axis? From 0 to -4 is 4, which means b is 2, because it's half that. I want the foci on my graph as well. And I also want to do eccentricity, so I need c. So c squared is a squared minus b squared, because a is the biggest. A was 3, so squared is that. B was 2, so squared is that. So c is square root of 5. Okay? Yeah, and so let's do eccentricity. We'll do that right now. It's just c over a. So square root of 5 over 3. Someone type that in. Does anyone have a calculator? All right, well, he's typing that in. Let's get our graph drawn. I need to put grids in here. What did you get? Let me see that. Okay, that makes more sense. It rounds to 0.75. Because I'm like, that is not 3/4. There's no way in the world that equals 3/4. And it doesn't. It equals 0.745 something. So it says it last period, and I just didn't check it. It's approximately 0.75. All right? So it actually is very much the eccentricity as the last example. All right, let's draw this thing. The center was here, to -2. A was 3. Which way did we go? Left to right or above and below? The endpoints were here and here. The major axes they're 3 to the right of and to the left of the center, weren't they? So just be careful you don't go the wrong way. So 1, 2, 3 to the right gets you that vertex that we were given. 1, 2, 3 to the left gets you to -1, -2 for the other vertex. If you go the other way, 2 above and 2 below. 2 above puts you on the x-axis. That was the 2, 0 they gave us. And then 2 below gets you this point. Go ahead and draw the ellipse. Now, I said I wanted to see the foci. The distance was square root of 5, which is 2 point something. So just come over here. This was 3 away, so go close to it. It was 2 point something away. And this one's also 2 point something away. There's your foci. Okay. Like I said, I think I'm going to put grids on here for the future, so you can get a better graph. But it's too late now. All right, we need the equation still. It'll be x minus what squared? Well, the center's at 2, -2, so x minus 2 squared goes here, and y plus 2 squared goes here, equals 1, because that's always a 1. And then a is 3, and squared is 9, which goes under the x because it's a horizontal ellipse. And then b is 2, squared is 4, and it's vertical, so it goes with the y. And there you go, we're done. Okay. Let's try this one now. Do you have this one? Let's not do that one. I think it's one I meant to leave off. that one instead, actually, for the future. Look at this. We have a nice graph of it, first of all. Is that the one they... Yeah, that's this one. Okay. But look at this. Just watch. If I wanted to find the eccentricity of this one, I need to find c first. It's going to be, that is a squared, that is b squared. So you get c squared is 1, or c is 1, which means eccentricity will be c over a, which is 1 over what? What was a? 3, because remember this is a squared. So I just want you to see that. You've got something that looks more circular in this case. Okay? The eccentricity is smaller. You know what? Let's change this up. Make that a 25. It's harder having the same numbers. All right. Center, -2, 1. A is 5. First, unfortunately, I made it too nice. B is 3. So C is going to be 4, because this is a 3, 4, 5 right triangle. That's the bad thing about making that nice, is the posts are going to be easier. So the vertices, I just want to write all this down without drawing the graph. Which way does this one go, by the way? Horizontally or vertically? Because the bigger is vertical. And so the vertices are above and below. So you have 5 above this point. Which point do you get? 5 above this. If you go 5 below it, you reduce the y value by 5. So 1 minus 5 is -4. There's your vertices. The foci on the same axis, so they go above and below, but now it's 4 above and below. So go 4 above the center for that one, and 4 below the center for that one. Let's go ahead and figure out the eccentricity. Which as decimal is 0.8. All right, let's draw this thing. -2, 1 was there. We're going 5 above and below. 1, 2, 3, 4, 5 there. 1, 2, 3, 4, 5 there. And then 3 left and right. You can see the eccentricity was closer to 1, and so we got a more elongated ellipse. So this is what I was saying before. If it's in general form looks like this. Everything's simplified. Everything's on the left. Our equation simply won't have an xy term. They just won't. And like I said, if you're missing either one of these square terms, you know it's a parabola. If you only have x squared or y squared, and you can say it that way. I just said if b is 0 or y is or a is 0. If they're the same coefficients, you get a circle. If they're the same sign but not identical numbers, you get an ellipse. So if they're 4 and 3, you get an ellipse. 4 and 4, though, it's a circle. And as I said, opposite sign is a hyperbola. And that's important because we don't want general form. You want to convert it into the correct form, the standard form for that shape, but you need to know what shape you're after because they have different standard forms. Okay? All right. You have this one? That's all we're going to do is convert the equation. Listen, you don't have to complete the square. You have to do one thing. What is that? You already got, you want to, just divide by 225. That's all you have to do. Here, watch. Just And then, by the way, 9/4 is $2.25, isn't it? 9 times 25 is 225. So this goes in 25 times, that simplifies like that. That goes in 9 times, so you get y squared over 9. And that's all we're going to do. I just wanted you to see the algebra. Just for the, just so you know, the center is the origin in this case, and it's horizontal. Here's a sketch what that ellipse would look like. Center is at the origin. A being 5, B being 3. So we're going to move on. Oh, there you go. All right, you have this in your paper. One thing I will mention is this is really how we expect an equation for a circle to be written. But you could write it as x minus h squared over r squared plus y minus k squared, also over y squared, r squared, equals 1. You know, divide through by r squared. And so I'm saying if you see an equation like this, it looks just like the equation for an ellipse, except for the denominators are the same, in which case it's actually a circle. But since the denominators are the same, it'd be better looking if you wrote it like this. Just multiply through by r squared. And so this is what we usually expect, although I don't think I'll take off if you leave in this form. Okay? Circles are really easy. Now, look, we're going to go a step further before we do an example. And let's talk about parametric equations. They're different. You can see totally different from a parabola. Parabolas are nicer in a sense because every parabola can be written either as y as a function of x or x as a function of y. And so you do that, and you just do the replacement like we did, and you get parametrics very easily. Circles, you can't do that. Ellipses, you can't do that. It is not a function. Y is not a function of x. X is not a function of y. You need to, it requires trig functions. Hyperbolas will have trig functions. Now, look at this. First of all, note that what you see is reality. I'm saying that's r, not r squared. It doesn't say the opposite of h. It says plus h. So that's nice thing about parametrics. You don't have to change anything from the graph. The other thing you should note is that you say you can put cosine here and sine here, but you could also put sine in the x equation and cosine in the x equation and the y equation, which is weird. You get the same shape either way, although you get a different starting point and direction if you switch it like that. Okay? And in fact, and by the way, over here in the ellipse, A being here means it's a horizontal ellipse. Of course, if it's vertical, A would be in the y equals equation. So those have to be in the correct equation depending on what kind of ellipse it is. The thing is, though, you could make these numbers, these coefficients, negative if you wanted, and you still get the same ellipse. So we'll play around with it like that. The normal way to do it is cosine here, sine here, both positive coefficients. You do that, that's kind of the standard way to do it. That's the easiest, but you don't have to. All right, here, let's do this one. Actually, you do this one. I want you to complete the square on this graph, okay? So, complete the square, you get the standard form equation. I want parametric form equation as well, though. And one thing I highly recommend before you do this, I'm just saying, be careful, because what you see in this equation is not reality. Either look at the graph or write the actual information down before you write the parametrics. So I'm saying put the actual radius here, which is 4. And I'm just going to do the normal way, cosine there, sine there. And then once again, reality is it is down 1 and left 1 and up 3. And so you put a -1 here, you put a +3 here, and it's easy. That's horizontal, it's vertical, so put the horizontal number there, vertical number there, you're done. Now, if we're talking about parametrics, then we need to show the starting point direction, right? So let's plug in t equals 0. What's cosine of 0? Miriam? Cosine of 0. I'll get to that. Josh? 1. Cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1. So when you plug in 0, you get 1 times 4 is 4, minus 1 is 3 for the x value. You plug in 0 here to get the y value. Well, sine of 0 is 1. 0, I said that. So you get 3, which is this point. 3, 3 is the coordinates for this point. So label that as your starting point, t equals 0. Now notice I'm plugging in pi over 2 next. Why? Because it's an angle. I'm doing trig functions. And so cosine of pi over 2 is 0. So this one you get -1 for the x value. When you plug in pi over 2 here, you get 1. Sine is 1 there. So you get 7. Which is this point up here, isn't it? Negative 1 comma 7 is the top. Which tells you you're starting on the right and going counterclockwise around the circle, which is exactly what you do on the unit circle, isn't it? So that's normal. If you want to do this the easy way, put both positive coefficients, make it cosine there, sine there, and your starting point will always be there, and you always go counterclockwise. That's the easy answer. But we're going to play around with it so you can see the other possibilities, but not on the first. All right, ready? Good. Let's do this one. What is it? Ellipse, circle, parabola, hyperbola, ellipse. Why? Because A and B are the same sign, but not equal. So we need to complete the square. Actually, not on the x's, though, just on the y's. Go ahead and factor out the 4. This is 32 over. It becomes positive. Don't forget to change that sign. And be really careful. The x is once again, I'm just going to bring that down. We didn't have to do anything with that. We're going to rewrite this as y plus 1 squared. Now, we add 1 here to complete the square, but what do I put over here? Because it's 1 times 4. Really, is we've added 4 to the right side. I mean to the left side, so we add 4 to the right side. Now, last step, divide by what? Remember, if it's an ellipse, it's supposed to be a 1 on the right side. That's what I'm saying. You have to remember your form so you know what your goal is here. So we said it's an ellipse, then we should have something of this form. X squared over something is 4. Y minus k squared over something, which is 9. And it always equals 1 on this side for an ellipse. Now the center is 0 comma negative 1, right? A is 3 and it's vertical. B is 2 and it's horizontal. All right, let's draw this thing. The center's here. Go, A is vertical, so go 3 above and 3 below. 2 left and right. Alright, so there's our shape. Now we're going to write the parametrics. And so you get to choose, and we're going to choose to make it weird. First of all, A was vertical, right? So the 3 goes here, and the 2 goes there. You don't have a choice about that. I'm going to choose to put sine in this equation, cosine in this equation, which is abnormal. So the center was 0 comma negative 1, so you don't put 0 there, but you do put the minus 1 there. And we're going to make one or both of these negative, just to also change it up even more. What do you want to do? Anybody? Negative 2? We'll go with that, okay? Like I said, whether you make these positive and negatives is your choice. Where you put sine and cosine is your choice. Everything else has to be exactly as I have it. So right now, we're going to figure out the starting point and direction for those equations. We'll start with t equals 0. If t equals 0, sine is 0, isn't it? And cosine is 1, so you get 0 comma 2. So it actually starts at the top this time. Now listen, we'll talk later about, there's some patterns here. You can figure out, so you can predict this, but for now we're not going to go there. If I plug in pi over 2, sine of pi over 2 is 1, so you get negative 2. Negative 2 times 1 is negative 2 for the x value. Cosine is 0 there, so you get negative 1. Negative 2, negative 1 is over here, which means it's going actually still counterclockwise, but with a different starting point. Okay? So that's all you have to do, really, to figure out starting point and direction. Plug in 0, and you get the starting point, of course. Plug in pi over 2. And when we say direction, we mean as t increases, which way are you traveling along that shape? In this case, it's counterclockwise, but it could have been clockwise. All right. I think we'll just stop there. By the way, what is that? We won't do it till Monday, but what is it? Right? There's not both. There's just x squared. So it's a parabola. That one, an ellipse. No, we're not doing that. I just want to show you some pictures. There's things called whispering galleries. And the idea is they build the structure. It's a room, an elliptical room, and at least the ceiling is elliptical, but usually the whole room is. And they put like this rail is at one focus, the other rail is at this focus, and it's a good ways across that thing. And you can whisper at one, be heard by the other, at the other one. The reason being, normally when you talk, the sound waves just go every direction, okay? And they just bounce off the walls of this room, and they dissipate. And whereas here, what will happen is, and this is a property of ellipses, like if you had an elliptical pool table, and you put the cue, like the dot there where you put a cue ball there, and the hole here, then you'll make it every single time, because any direction you hit it, it's going to bounce off this, go hit the other focus, no matter which direction. So that's what's happening to the sound waves. They'll get focused on the other focus. So all the sound waves that you're coming from you, all go there, instead of just begin bouncing everywhere. And so that's why you can hear. And you'll see that in architecture. So if you're over here, you got to be careful because they can hear you over here very easily. By the way, I was mentioning Australian football. Cricket also uses, but that was Australian football field. That's cricket field. Just for the record, rugby is kind of similar to Australian football if you look it up. But rugby is played on a rectangular field, whereas Australian football is not. It's on an elliptical field. I'm not sure which one that is. There's an American football field. Okay. There we go.